Welcome to this last segment of the lecture on counting rules. Previously we discussed the product rule and the sum rule. So in this segment we're discussing the third fundamental counting rule for combinatorics, and that is called the inclusion-exclusion principle. So here is the statement of the rule. Let's say A1 and A2 are sets. Then the cardinality of the set A1 union A2 is, according to this principle, the cardinality of A1 plus the cardinality of A2 minus the cardinality of the intersection of A1 and A2. So let's illustrate the validity of this principle using a Venn diagram. That's not a proof, it's just an intuition for why it's true. So let's say you have a set A1 and a set A2, and you want to count the total number of elements that are either in A1 or A2 or both. So according to this calculation, you're going to first take into account the elements of A1. So you're going to count all the elements that are in blue here, that is in that set. Then you're going to add all the elements, or the total number of elements in A2. So these are the elements that are shown in red here. Now here's the problem. All of the elements that are in the intersection of A1 and A2 have been counted twice. Notice they are both in blue and in red. And that is the reason why we need to remove one copy of all of these elements. And how many of them are there? Well, the cardinality of the intersection. So this is the intuition for why this principle holds, and it's called the inclusion-exclusion principle, because you first include all of the elements in blue and then all of the elements in red, and then you exclude one set of the elements in the intersection. So, as our first example of an application of the inclusion-exclusion principle, here is a quick survey that I used to perform in the classroom when I was using the traditional method before I switched to the flipped classroom. I wanted to know how many students in the class were either on Facebook or Google+. So I would ask students, raise your hand if you're on Facebook. Let's say I had a class of 30 students. Then a typical response for Facebook would be something like 23. And then I would ask, how many of you are on Google+? And a typical answer out of 30 students would be about 7. So, notice the total number of answers is 23 plus 7. So according to the sum rule, this makes sense because I had 30 students in the class, and apparently every one of them is either on Facebook or Google+. But wait a second, that doesn't make any sense. What I did is I asked them a third question, and I said, well, how many of you are on both Facebook and Google+? And then I get an answer of 4. So there were 4 students who had an account both in Facebook and Google+. So what does that mean? What's the final answer? How many students are on either one of the two social networking sites? Well, the answer is 23, which is the cardinality of the first set here, the set of students that have an account on Facebook, plus 7, which is the cardinality of the set of students that have an account on Google+, minus the cardinality of the set of students that have an account on both systems. So the final answer in this case was 26, which means there were 4 students who had no account on either site. So this is a very simple application of the inclusion-exclusion principle. Now let's look at a second example of an application of the inclusion-exclusion principle. How many bit strings of length 5 start with a 00 or end with a 1? So here is a skeleton for all the possible 5-bit strings. And notice we have an or here. It's not an and. So one possibility is the string starts with a double zero, and another possibility is that the string ends with a 1. So let's count how many strings in this category. We can use the product rule because 2 of the bits are fixed, so we have 2 choices for each one of the 3 remaining bits. In other words, we have 2 to the 3 strings in this category. And similarly, for this category, we have 4 unspecified bit positions. We have 2 options for each one of them. So according to the product rule, we have 2 to the 4 strings of this type. So to answer then this question, we can simply add these 2 numbers. Well, no, actually we can't. Notice in particular there are strings that are in both categories. So these 2 sets do overlap. So you can't use the sum rule here. You have to use the inclusion-exclusion principle, which means you have to subtract the total number of bit strings that are in both of these categories. So what do these strings look like? Well, they must start with a double zero and they must end with a 1. So how many of those are there? Well, there are 2 unspecified bit positions. You have 2 options for each one of those, so the answer is there are 2 to the power 2 of them. So the final answer then to this question is 8 plus 16 minus 4 is 20. Now, I strongly encourage you to double-check your answers whenever possible, and in particular, if there are 2 different ways of computing the same answer, then this is a good way to check your work. So here is example 2 prime. It's basically the same question as example 2, but now I want you to solve it in a different way. In fact, I want you to solve it using the complement rule. So the answer that we want, which is the total number of bit strings of length 5 that start with 0, 0 or end with 1, according to the complement rule, it's the total number of 5-bit strings with no constraints minus the number of strings that do not satisfy this constraint. So what are these strings? The ones that don't have this property. Well, if they don't end with 1, then they must end with 0. So that's one property that they all share. Now the second property is that they cannot start with 0, 0. So what does that mean? Well, they could start with, say, 0, 1. But they could also start with 1, 0. And they could also start with 1, 1. These are the only 3 possibilities. So I can wrap it up here. Now the question is, what do we do with those 3 numbers? Well, it should be obvious that none of the strings in this category can belong to any one of these 2. And in fact, the 3 categories do not overlap, because if you start with 0, 1, you can start with the other 2 options, and similarly for the other cases. So here we can just use the sum rule to add up those 3 numbers. Now, before we compute this final answer, let's make sure we understand what we did here. Remember, this is the total number of bit strings that do not satisfy this condition. In other words, it's the total number of bit strings that satisfy the complement of this condition. And notice we have an OR here. So if a bit string does not satisfy this condition, what does that mean? That means it must end with a 0, and it must start with something other than 0, 0. And these are the 3 options, the non-overlapping options that we just discussed here. So let's wrap up this computation by computing first the total number of 5-bit strings. That's 2 to the power 5, or 32. How many strings of this kind do we have? Well, there's only 2 unspecified bit positions, so we have 4 options here. We have 4 options here, and similarly 4 options for the last one, for a total of 12. 32 minus 12 is 20, and we get the same answer as the one we got for the previous approach. So, this concludes our discussion of the inclusion-exclusion principle, and together with the product rule and the sum rule, that concludes our discussion of the three fundamental counting rules for combinatorics. Now, a couple observations. First, about the inclusion-exclusion principle. There's a more general version of it that applies to more than two sets. In fact, it applies to n sets. We're not going to have time to cover it here, but you can look it up if you want to learn that more general principle. And the second final observation is that in addition to those three counting rules I just mentioned, make sure to remember the complement rule, which, as we discussed, can come in very handy on some examples.